Uh, Now I am going to discuss about the chemical reaction kinetics. As you know that our fermentation industry is the, or biochemical industry, one of the major unit that we have, that is the bioprocess, and in the bioprocess, that the biochemical reaction that take place. Now question comes that how the reaction take place. To understand this mode of reactions and how to study the kinetics of those reaction, first we should know how the chemical reaction take place, how we study the chemical kinetics, then we can come to the biochemical reaction kinetics. So so today I want to discuss the chemical reaction kinetics, and here I want to tell that this reaction usually take place in a reactor, and reactor basically is a vessel where the chemical reaction take place, and bioreactor basically a vessel in which the reaction take place in presence of the biomolecules. So so first I want to give the overall this that what is the classification of the chemical reactions. We have this all the chemical reaction can be classified in two different class. One is called homogeneous reaction, another is the heterogeneous reaction. Now what the question comes, what is homogeneous reaction and what is heterogeneous reaction? Now homogeneous reaction means if the reaction take place, we know there are three different phases. One is gas, another is liquid, another is solid. If the reaction take place in only one phase, we call it homogeneous reaction, and mostly that in the solid actually there is no reaction take place. So mostly the reaction take place either in the gaseous phase and liquid phase. If the reaction take place only in the liquid phase, we call it homogeneous reaction. If it take place only the gaseous phase, we call it the homogeneous. Now examples, suppose the ammonia formation with the help of nitrogen and hydrogen. This is all are gas, because the nitrogen is gas, hydrogen is gas, your product also ammonia also gas. So this is a pure what we call homogeneous reaction. Now we have different examples of the enzymatic reactions. As for example, I told you the glucose, when we convert it to fructose, because fructose we know it is 10 times sweeter than glucose, and this is largely used for the diabetes patient, and we use the enzyme called glucose isomerase enzyme. So naturally that the all are remain in the one phase, liquid phase. That is why we call it homogeneous reaction. Now next is the heterogeneous reaction. Heterogeneous reaction means it should contains the more than one phase, because either the minimum two phase should be present in the reaction mixture. I can give a very simple example of the burning of wood, because when wood we burn in presence of oxygen, it produces carbon dioxide and water. So you know that your product is gas, your wood is solid material, burns and react with the oxygen that is in the gaseous form. So this is an example of the heterogeneous reaction. Now we talk about the microbial reaction, microbial fermentation process. In the microbial fermentation process, what we are basically do, we use the microorganism. The microorganism, they are insoluble mass, that then they usually take the soluble material from the fermentation broth, and they use for their growth and metabolism purpose, and we get our desired product. So this is the example, because the one is your burning of wood, another is the microbial fermentation process. That is the example of heterogeneous reaction kinetics. Now question comes, how it is differed from the homogeneous reaction. Now in case of heterogeneous reaction, what is happening, since there is a presence of two phases, one phase should come in contact with the other phase, then and only then the reaction will take place. Otherwise no reaction will take place. So you know that so when the one phase come in contact with the other phase, we call it diffusion. This is they diffuse to the surface, and then when they react and form the product, then again it should diffuse back to the bulk. So you know that diffusion phenomena plays very important role in the heterogeneous reaction process. So here two things simultaneously take place, the diffusion as well as the reaction. Now a very interesting thing that if the diffusion rate is more as compared to rate of reaction, then reaction is the controlling factor. So because what do you mean by that? Because if we want to improve the rate of reaction, the rate of product formation process, then what you have to do, we shall have to improve the reaction rate. Then you can get the more product when your rate of diffusion is more in case of rate of reaction. Now in case of reverse, if your rate of diffusion is less as compared to rate of reaction, then you have to increase the diffusion so that your product formation can be increased. So these are the things how we can handle so to get the more product formation in the process. So now the reaction that I am going to discuss here, that the simple reaction and how we can analyze this reaction. This is I want to give you very typical examples, one or two examples that I shall give you. This is the AA plus BB with the RR and SS. This is if you write the rate of disappearance of A, it is minus RA equal to minus dCA by dt by d. Why minus? Because the A is the substrate. As the reaction take place, then with respect to time, if you look at the profile, that they keep on decreasing with respect to time. So rate of degradation of the substrate is considered the negative profile, and rate of formation of the product, this is a positive profile. It can keep on increasing with respect to time. Now if you look at rate of formation of R, obviously it will be plus. This will be dCR by dt, rate of formation of, that is also the rate of formation of product that we can write. Now if we want to correlate all this rate of reaction, I can write like this: RA by A equal to minus RB by B equal to RR by R and RS by R. This is how we can equilibrate this reaction. Rate of reaction influenced by the composition and the energy of material. Energy means temperature, light intensity, magnetic field intensity, etc. So these are the different. Now here I want to again point out the unit of this is very important. This is Ca is the concentration of A, and Ca is concentration of A usually expressed moles per unit volume, moles per liter. Moles per, it can be expressed in other way also. It can be expressed mass per unit volume, grams per liter. It can be used any kg per cubic meter, whatever it is. And time can be expressed in seconds, minutes, hour, whatever we can. This is how we can express the rate. Now here the rate of suppose a simple rate of reaction, how we can write? So A converted to B, how we can write this rate expression? Minus RA equal to K into Ca to the power n. What is K? K is the rate constant, and what is the n? In the order of reaction. Now both are the experimental parameter, and how this experimental, I will show you how the experimental parameter we can determine. And K again depends on temperature. As per Arrhenius equation, this K equal to K0 e to the power E by RA. And I was talking about in the last class, I was talking about the E is the activation energy. So and that if we study this reaction at different temperature, then we can determine the activation energy of the particular reaction that we can determine. Now let me come back here, that when there is a nth order reaction, the expression is this: minus RA equal to minus dCA by dt K into Ca to the power n. If you take the log, it will be what? Minus log minus dCA by dt equal to log K, this is K, plus n, this is n will come here, in log Ca. Am I right? So this is equal to, this is nothing but similar to your straight line equation. This is y equal to mx plus c, because but only the problem is that this here you have to plot the log in the log graph paper. because this is log minus dCA by dt, and this is log because this is constant. The k is constant, k is not the variables. So Ca is the variable. So you have to plot log minus dCA by dt versus log Ca, and then if you plot it, then you'll get a slope, and slope we can find a slope here, and this slope will give you the value of n, and intercept will give you the value of ln k. This is then you can find out the value of k. Now here I want to point out again that if you look at the unit of k, also very important. Now here we have mentioned here the what should be the unit of k. The unit of k depends on the order of reaction. As the order of reaction changes, unit also changes. As for example, if your order of reaction is zero order reaction, then this will that moles per liter per second. If the order of reaction is the first order reaction, then this will be 0, then it will be second inverse. If order of reaction is 2, then it will be inverse, the mole per liter inverse into second inverse. So you know that, so unit of k depends on the order of reaction. This is very important. Now in the biological system, we have previously I was discussing about the irreversible reaction, but in the biological reaction, if you look at most of the biological reaction, they usually take place reversible. They are reversibly. Reversible means they have a forward reaction and they have a backward reaction. You see, there is a forward reaction, there is a backward reaction. Now and since there is a forward reaction and there is a backward reaction, at equilibrium conditions, what will happen? The rate of forward reaction should be equal to rate of backward reaction, and under this equilibrium condition, what will happen? That if these are equal, then I can write this is equal to CR by Ca. CR, what is CR? Concentration of product. What is Ca? Concentration of substrate. This is equal to K1. K1 is the rate constant for the forward reaction. K2 is the rate constant for the backward reaction. So this ratio is considered as a equilibrium constant, is Kc. Kc is the concentration of product by concentration of reactant. Now here I want to point out, suppose since the biochemical reactions, they mostly this reversible in nature. Now question comes, how we can increase the production? We can increase the production that in two ways. As soon as if we increase the amount of substrate that in this system, then we can get more product, because this ratio Kc is constant. Kc is equal to concentration of product versus concentration of substrate. More substrate, more will be product. Less substrate, less will be product. The another way we can increase the substrate concentration, the product concentration, as soon as the product form, if we can take it out. Some other means, as for example, ethanol, when it forms, ethanol can be volatilized out at a vacuum. At a low temperature I can take it out. So more glucose can be converted into the ethanol. So you know that so in the reversible reaction 2 approach, through which we can increase the product concentration, either you increase the substrate concentration, or as soon as the product form, if you take it out from the system, then we can increase the productivity of the process. Now that reaction, this aim is now I can consider this is CR0 by CA0. CR0 means initial product concentration, CA0 is the initial substrate concentration. Now if we analyze if you write the previous equation, that dCr by dt, what is dCr by dt? Is the rate of product formation, equal to minus dCa by dt. What is minus dCa by dt? Rate of substrate degradation. This is equal to, I can write Ca0, because what is Ca? Ca is the concentration of substrate at any time t. At any time t, let us have if the conversion factor is the ratio is the Xa, then this will be nothing but Ca0 into Xa. But Ca0 is constant, so that will come out here, and so your equation will be dxa by dt. This is equal to K1 into Ca minus K2 into Cr. Now K1 into Ca can be written as Ca0, because Ca0 is the initial substrate concentration, and Ca0 is the initial substrate concentration and the how much is it converted. So this multiplied, if you Ca0 initial concentration and how much is converted, the difference will give you how much that substrate that remain. That is here, and here what is the m into Ca0 is what is the C art 0. Am I right? This is the initial product concentration, and plus this is the whatever conversion take place, that is Ca0 into Xa. So this is the product formation take place. So K2 into this. Now at equilibrium this will be equal to 0. So I can write this is equal to, this equation can be written like this. Now let us do some analysis of the irreversible reaction also. This is the simple first order reaction. This is we consider A into B. A is the substrate and we are getting the product. I can write like this. Now how we can analyze this? This is we analyze the dCA by dt into I can take this Ca. I can take the Ca here. I can take Ca here and K into that into 0 to t the dt here. Now this is equal to ln say minus ln Ca by Ca0, integration Ca0 to Ca. This is equal to K into t. The conversion factor, I told you Xa equal to Ca0 minus Ca by Ca0. That is how much product is a fraction of the substrate that is converted into product, and this is equal to dx by this we can convert to this is nothing but Ca0 into that this we can write in the form of dxa by dt equal to k into 1 minus xa. We can put this here, we can write in this form. Now another thing that I want to point out that in the biochemical industry, the biochemical metabolic processes, mostly they are the chain reaction and the reversible reaction. Now question come how we analyze the chain reaction. That so first of all let me show you this is the chain reaction. This is A to B, B to C, C to D, like this is the chain reaction that we have. And if you look at the A, this is Ca, that is the first component will keep on decreasing with respect to time. Am I right? And if you look at the B, C, D, then B formation take place, then again decreases. And as soon as the B formation take place, C formation take place, C formation and decreases. Then again the D formation take place, and then again E form, and finally that product that we have E, this will keep on increasing with it. This will not decrease. This will keep on rising with respect to time. So this is the kind of profile that we have with respect to different substrates. That different that composition of the reaction mixture, how the different metabolites formation take place. Now why I am showing you this, that our intention is to find out, suppose we are interested for this compound B. Now we are interested to find out that at what time the Cb will be maximum. Suppose I am interested to with the metabolite C, then I am interested that when the C formation will be maximum. If I am interested in D, then the question comes that when the D will be maximum. So this intermediate the chain reaction, if we do the analysis, we can easily find out that at what time we can get the maximum this intermediate product formation will take place. And this is the final part of final product formation. Now let us show you the analysis how you can analyze the this chain reaction. Suppose I have taken into consideration a simple reaction A to B, B to C. The A to B, let us assume this is the rate constant, this is small k, this is not capital K, and this is small k2, this is the rate constant for the B to C. And let us assume they are all irreversible reaction. We assume that then rate of formation of rate of degradation of substrate A, it will be equal to K1 into Ca. Am I right? Now rate of formation of B will be something different. Rate of formation, how you can calculate the rate of formation of B? Because rate of formation of B is that rate of formation of B minus the rate of degradation of B, because two things simultaneously occur in the intermediate compound, rate of formation of B and rate of degradation of B. So if you look at rate of formation of B, the K into Ca, and rate of degradation of B is the K2 into Cb. So this is how it can be written, and rate of formation of C always we can write like this, dCa by d K2 into Cc. So this is how the rate expression we can write for all these different steps: rate of formation of A, rate of formation of B, rate of formation of C, how we can write like this. Now one thing I can assume, the Ca0, what is Ca0? Ca0 is the initial substrate concentration. This is equal to, since it is the equimolecular conversion, I can write Ca0 equal to Ca plus Cb plus Cc. This is like this. I can write that. So at the 0 point there is no nothing, no B and C is there, but that's the time of reaction take place. Then C will be converted to B, B will be converted to C. So but Ca 0 will remain constant. Ca 0 will be Ca plus Cb plus Cc. Now if you look at the first reaction, that rate reaction we have, this is, I can write what ln Ca by Ca0 K1 into T. Now this equation, that if you write this equation, I can take the Ca here, dCa by Ca minus K1 into dt. Am I right? And this is equal to dCa by Ca is d ln Ca. Now d ln Ca we can integrate Ca0 to Ca. Then this is 0 to T. So we can write, what we can write? This is, we can write, this is ln Ca0 to Ca0 and into K1 into T. Now if you so what will be the value of C? Ca equal to Ca0, because this will be e to the power minus K1T, and so this is so this equation will give you the concentration of A at any time t. So suppose if I know the value of Ca0 and if I know the value of K1, the rate constant of the first step, so if we simply put the value, the time, the 5 minutes, 6 minutes, 7 minutes, 8 minutes, so you can find at different times what is the concentration of Ca that we can easily determine on the basis of this equation. Now let us come to the second part. Now we have seen second part is that rate of formation of B is equal to K1 into Ca minus K2 by Cb. Am I right? Now this I can write, because here Ca I can already we have determined Ca equal to Ca0 e to the power minus K1T. So I can write like this. Now here if you look at this, I can again change over this side, and then we multiplied both sides by e to the power K2T, and if we multiply it by K2T, it will come like this, and finally we get this. Now if this is equal to that dCb e k to the power K2T by dt equal to K1 into Ca e to the power K2 minus K1T. So this is equal to, then Cb will be equal to K1 by K1 minus K2 into this. I can write like this, and this will be constant, plus constant. Now what is the boundary condition? Boundary condition is that when t equal to 0, Cb equal to 0. So t equal to 0, Cb equal to 0, then this will be 0. Then constant will be equal to this much. Only that sign might be changed little bit. That so I can write this constant is like this, and putting this value, then this equation will comes like this, and simplified form Cb is like this. So from this equation I can easily find out the correlation between the concentration of B at time t, because you see all are constant. The K1 is constant, K2 is constant, Ca0 is constant. So if you want to find out the value of B at any time t, you just put the value of the time here, you will get the value of Cb. Now initially you can remember that I have written that Ca0 equal to, I have written Ca0 equal to Ca plus Cb plus Cc. Now you have the expression for Ca, you have the expression for Cb. So Cc you can easily find out because this is constant. So Cc will be equal to Ca0 minus Ca minus Cb. So I can easily find out that. Okay. Now question comes, how you can find out the T max, at what time the Cb will be max. If you look at this figure, that here this is the profile of Cb. Here when Cb is maximum, then this Cb by dt equal to 0. Am I right? So what I can do, I can differentiate this with respect to with time, and we can get this equation, and this should be equal to 0. And if it is equal to 0, then this cannot be equal to 0. So I can write this equal to this equal to this we can write. And if you write this equal to, then T max will be equal to this. Now initially we have this equation that already we derived. I have already derived this equation. Now in this equation, if we put the value of T max here, then we can easily find out the Cb max. So this is how we can find out the T max and Cb max of the chain reaction. This is largely applicable in the biochemical processes. Thank you.